In the previous videos, we have seen how materials have a significant impact on the fire spread hazard that a shelter presents to its neighbours. Another factor that has a significant impact on fire spread is wind. Because we were testing outdoors, none of the experiments took place in completely identical wind conditions to one another. This provided us the opportunity to observe some of the effects of wind speed and direction. We also benefited from a couple of days of very high wind, which allowed us to perform some additional tests under more extreme wind conditions.
We're bringing the heat today. It's a little bit different. It's cool. I wasn't so excited when we were going to do this burn, but it's pretty cool.
The first opportunity to look at the effect of wind speed comes from the timber wall shelter with the sheet metal roof. We conducted this test 3 times to examine the repeatability of our experimental process, with each of the 3 tests occurring in slightly different wind speeds. Fortunately, the prevailing wind direction was the same in each experiment, coming from the back left corner of the shelter behind the door. We can look at 2 of these experiments to show how wind can impact fire spread. There are several good visual indicators and data readings that help us to compare how wind impacts each test.
Because I've just remembered it and because it's extremely important, don't stand on this hose, okay? That's item number 1 for today, is don't stand on the hose. I'll explain why.
Sorry, can I just point out you're standing on the hose?
You're going to hear Sam, for example, talk about how cool a fire test was, and that's coming from a very scientific place. We're in the middle of a farm studying fire in a safe environment, which is very different than being in an informal settlement when this is a real fire.
In this first case, the wind is at a relatively low speed, less than 3 kilometers an hour on average. In this experiment, the smoke plume rises almost vertically. The flames projected from the window and door are often large, but generally project upwards rather than outwards. The heat flux gauges 2 meters from the door and window capture the thermal exposure near the door and window flames. Both gauges registered heat fluxes that would be able to ignite many materials given a reasonable time of exposure. When the shelter was burning at its most intense, the heat fluxes recorded on both the door and window side reached 40 kilowatts per meter squared. We'll compare this number to the windier case in a moment. However, our footage shows that there were no moments that the flame was tilted by the wind, resulting in no direct flame contact on the gauges. This can be contrasted with a test with a slightly stronger wind. At just over 6 kilometers an hour on average, this is not a particularly strong wind, but is enough to have an impact on fire spread potential.
Oh, some nice flames outside there.
In a moment, we will look at the heat fluxes and external flames, but the first thing to note is that this fire was actually cooler than the first fire. In the first shelter, we recorded temperatures up to 1100 degrees Celsius. However, in this windier test, the temperatures were closer to 900 degrees Celsius, a considerable drop. This is likely due to the wind helping to ventilate hot gases out of the shelter and reducing the amount of burning inside.
We've got absolutely enormous flames from the door, reaching at the moment about 2 meters.
However, context always matters, and a cooler fire does not necessarily mean it's safer or less likely to spread. The wind has the effect of producing large external flames from the door side of the shelter. Any neighbouring shelter placed here would be at extremely high risk of ignition. Remember that the heat flux at the door gauge in the first test was measured at 40 kilowatts per meter squared, but with no flame impingement. While in this test, the heat flux reliably stabilizes at the same level of heat flux, 40 kilowatts per meter squared, but then with added momentary jumps up to over 60 and even 70 kilowatts per meter squared when the flame projects towards and contacts the gauge, almost double the thermal exposure of the first test. On the other hand, the wind slows down the burning of the back and side walls and reduces the maximum heat fluxes to the window gauge by over half, vastly reducing the likelihood that a shelter here would ignite. so it's easy to see how wind can push fire spread rapidly in one direction through a settlement, whilst almost preventing fire spread in the other direction. More extreme winds were found to have a stark impact on other types of shelter. During the experiments, we had opportunities to do high wind speed tests of the metal sheet and bamboo mat shelters that we had previously tested at lower wind speeds. Unfortunately, due to the high winds, we couldn't set out our instrumentation rigs, so we weren't able to capture heat flux data around the shelter, but some qualitative findings are possible. In both cases, the wind came from the door side of the shelter, so long flames were projected from the window side. In the case of the metal sheet shelter, the wind averaged 18 km an hour, with some gusts up to over 40 km an hour. The fire reached flashover, the period of very rapid fire growth, about 3 minutes faster than the previous low wind test, and persistently long flames up to over 3 meters were projected from the window. In the bamboo mat test, the wind averaged 17 km an hour, but with gusts up to 32 km an hour. This fire reached flashover about a minute faster than its low wind counterpart. In this test, large flames projected from the window side along the entire length of the wall as the bamboo mat burned away. There remains much more to explore about fire and wind. For example, we did not get the opportunity to test thatch roof shelters under high wind speeds, though we did observe that even at low wind speeds, the flame plume can be significantly tilted over. In theory, every combination of materials would need to be tested at a range of wind speed and directions to have a complete and robust understanding. However, it is easy to see why wind is such a driver of fire spread in settlements. Our experiments indicate a variety of impacts, including the potential for faster fire growth rate and large deflected external flames as the wind speed increases. As a natural phenomenon, wind will always remain a persistent factor in fire spread and should be something that is considered seriously in settlement fire safety measures. Though there is much analysis of our experimental data still to be done, watch the next video in our series to find out how we might start approaching the integration of technical findings with existing guidance for shelter and settlement planning.